Hello, this is Jeremy Colmel, and today I'm going to be talking about FluoroMatch Visualizer. This is a platform where you can visualize your PFAS non-targeted data and be able to start confirming identifications, as well as discovering unknown compounds. Now, in order to use this software, first you have to run FluoroMatch or FluoroMatch Modular or FluoroMatch Flow. These software you can download at Innovative Omics at FluoroMatch if you click here. And if you get the 2.6 or later version, which will now be uploaded to the website, it will also come with FluoroMatch Visualizer. In order to use FluoroMatch Visualizer, after you run FluoroMatch Flow or FluoroMatch Modular, you have to use those outputs and a Power BI file that comes with FluoroMatch Flow. First, you'll have to download Power BI Desktop, which is also free. And it can be downloaded at powerbi.microsoft.com/en-us/desktops. Then click download, and then download that app on your desktop. Once you've downloaded it, then navigate to your FluoroMatch folder that you've unzipped, and double-click FluoroMatch_Visualizer, and then double-click the Power BI file. Or if it's not opening up with Power BI, you can go Open With and Power BI Desktop. Once you've opened this file, then you have to also import your data. So you'll go to this icon over here with the little pencil and table, Data Source Settings, and then you'll change these neg_raw msms.cfe and neg_id_fin files to the ones in your output folder after you run FluoroMatch Modular or FluoroMatch Flow. So you go to Change Source, Browse, find the output file, and then again take neg_raw msms, and then neg_id_fin, capital Fin. Open that. You'd press OK. I'm pressing cancel now because we already have the data uploaded. Then you'd press close, apply, and it will load in your data. If there's any issues in loading, they'll usually tell you that some column name was off, so rename your column name, whether it be in the MSMS file or the neg_id_fin file. Or you can click on this Power Query Editor, go to whether it's the neg_raw MSMS or the neg_id_fin, and it'll have an exclamation point, and you can find out where the error is. Usually it's in these promoted headers or change type. For example, let's say your file didn't have ppm_error. You'd have to either delete this or add a column, etc. If you have any issues with Power BI, you can contact me. Look at innovativebomics.com to find contact information. Now, once you have your data in, there's a lot of very exciting things you can do with this tool to start annotating. As you can see, it's pretty hard to understand these different plots when all the data is showing at once. But let's walk through what these plots mean, and then we'll go in detail with some examples. This plot is a nominal Kendrick mass normalized to CF2 with a mass defect normalized to CF2. Note that advanced users can also change what this mass defect is normalized to. So for example, CF2O or some other series. But generally, it starts with CF2. Now, anything that forms a straight line in this Kendrick mass defect plot is going to belong to one series. So let's say, okay, we have these purple dots here. You can scroll over them, and it shows that it's a sulfonic acid. This is a C10 sulfonic acid. This would be our C9, so on and so forth. So let's say we want to look at this series. If you click on one dot, you can see that it's CF2N35. In order to choose a specific series, you have to go to these series types identifiers, search for it in the search bar, so you could type 35, and then select. To refresh, you can click on any box in case something is selected. Now, you can see how a Kendrick Mass defect plot works even better. Here you can see that they're all forming a straight line in Kendrick Mass defect space. The reason for this is that CF2, since the mass defect of CF2 is 0, because we've normalized it to CF2, then things that differ only in the number of CF2s will have exactly the same mass defect. So for example, if I scroll through these, they all have the same number, they all have a sulfonic acid and only differ in the carbon-fluorine chain length. Now you notice that if there's not a structure assigned, you'll get this stick figure. So this is our nothing was found image. Now if you look at the next plot over, this is the retention time versus mass to charge plot. And you can see that it forms a really clear pattern. Whereas you increase in mass, you also increase in retention time at a fixed rate, so it forms this line. Note that this will not be a completely straight line depending on your chromatographic gradient, etc. And so, given this pattern, we can be somewhat sure that all of these PFAS, or PFSAs I should say, are probably real. In order to truly confirm a PFSA, we'll have to look at its MSMS spectrum. So if I click one of these dots, now I can see it. All other tables and plots are now updated to show information just for this one feature. Note that in any of these plots, you can zoom in and zoom out using these little dots. So let's look at the third piece of information, which is this MSMS spectra. The little red diamonds show that a fragment has been annotated. So you can see clearly here that all the major fragments are annotated. Some of them are quite low, as you can see here, but if we zoom in, we can see that they still are probably real fragments. You can set your thresholds when you're running FluoroMatch, so that will decide what you actually see. Let's say you're zoomed out and you want to find out what these fragments are. You can just simply scroll over one of these diamonds and it will show you. This is a C4F8SO3, for example, C3F6SO3, C4F9, C3F7, C3F7. So these different fragments. Generally, you'll often see some very clear patterns. So for sulfonic acids containing PFAS, for example, you can also look over the spectra itself. So if we scroll over this one, you'll see SO3, which makes sense. And it's a very high abundant fragment, which is representative of the sulfonic acid group. Then we have SO3F, which means we have a sulfonic acid group on some kind of fluorinated species. And then we have a C2F5 as the next abundant, meaning we have a carbon-fluorine chain probably of 2 lengths and more. So these low abundant fragments are especially important because it's less likely for other formula to match them. So using this MSM information, I can be pretty clear that this is a sulfonic acid PFSA, and then because it's matched to exact mass as well, it most likely is C6 sulfonic acid. And so on and so forth. You can start scrolling through. Again, you can see some of these clear patterns over and over again for this group SO3, C2F, SO3, SO3F, so on and so forth, which starts to give you an idea that you're confident. Note that if I click on one of these frames and it refreshes, now you get the average spectrum for the entire series, which can be helpful in determining what fragments show up for that homologous series and whether a member actually fits into that series and has the same fragmentation pattern. Note you'll also see over here a table that's sorted by the most intense sum of the fragments for all of these series, and then so on and so forth. So you can see that this C8F17SO3, which is probably just the N-H for PFAS, is the most abundant, followed by C6F13. But as far as fragments go, SO3 and SO3F are some of the most dominant fragments, plus unannotated fragments. CF2SO3 is the next one, so on and so forth with some chains. If we want to see all of the members in the series that have a certain fragment, we can click that fragment, and now it shows all of those members that contain those series, those fragments. So that's a very useful tool over here. Note that if I control click SO3F and SO3, now I'm seeing all the species that have either of these fragments. If I want both, I can click End, which will show me that they have to have both of those. And may be too restrictive in certain cases. So I could walk through these series. In this case, like I said, and let's say we want to refresh this, so we don't want to show the fragments, we can click around again on some of the boxes and eventually it will just refresh. Now, let's say that I want to do my final statistics on FluoroMatch. Something I'd probably start doing now is opening up PowerPoint or a notepad or something and start writing down the series that I'm confident in. Start taking a list, maybe you do in Excel, however you want. So I might start here and I'll say, okay, we have a PFSA series, and that's going to be 35. And I'm going to say all are correct, which is unusual. Now, let's say we want to look for more series. We can unselect CF35. And again, now all of the series are showing again. You can see here that it's AFFF, so most of the things we see are actually PFAS. You can see many different series here. And so you can just manually start clicking on different ones and go one by one, which is a very useful method. Another way is especially more complex matrices with less PFAS, where this might be even more noisy and you can't easily see series. You might want to start with the most confident. So you'd select A. Note that in not all data sets, depending on your abundance of PFAS, will you get even any A's or a few A's. But that's a great place to start when you have them because they're very confident hits. Based on our studies, only 5% are false positives. So this is a great way to go down and filter through series. You can see that there's some outside of the range that I thought most PFAS would occur. Now, let's find another group that's A. Okay, so here's your carboxylic acids. Another commonly expected PFAS. So this one belongs to 52. As you can see, when you scroll over, you can see CF2 and 52. So again, I'm going to type in 52 and go into these series. Notice that now, because I filtered by A, there's only a few showing up. So I might want to select all of the scores to see all the members of a series. You can see some interesting things like here. So for example, this whole range is definitely outside of that diagonal pattern that we mentioned, that we should be able to observe. These ones also seem to be outside of this diagonal pattern. If we look at these, they're all C+, meaning that they had no MSMS information, or if they did have MSMS information, it wasn't matched to anything. So, given that they're C+, and that they fall out of this diagonal, which is very important, they should all fall within this diagonal, these are probably false positives. Same thing over here, we can look at and see if everything seems to be C+. We do see a B-, which means that there was some fragmentation annotation, but again, pretty low confidence, and it is a high mass fragment. that could be matched with other kinds of formulas. So again, not necessarily a PFAS and definitely probably not a PFAS. So here we can see, okay, there's a bunch of noise out here. There's a bunch of noise out here. Maybe these as well. So something we can do again is start to select by a type of fragment. So usually we try to stick with low mass fragments for confirmation. So if I click C3F7, now you see that most of those within that diagonal are stayed, and all of those, if we refresh outside of that, are removed. So I'll add some other fragments as well. That seems to cover our entire. So in this case, when we're taking our notes, we may want to export this table and only include those feature numbers here. And this even looks a little out of range. So let's just see. It's MSMS spectra. Seems to have a lot of annotated fragments. C3F7 being fairly abundant. C4F9 also being fairly abundant. So I might be somewhat confident in the species actually. So we can start filtering by those that contain some of these fragments and then just export this table. You can go to copy visual won't, but you can go to here, export data, and you can export it wherever you want. Let's say our desktop. And here you can see the table that has our features. Now, these features are going to be pretty important because eventually we'll want to filter out our final MSMS table by these features. What I mean by that is if you go to neg ID'd fin, which is your final table, and then you start compiling a list of these features that you've confirmed, one thing you can do is you can go here, insert, highlight these, highlight those that have been confirmed, and then you have to find the identifier. Should be row ID over here. You can go to home, conditional format, highlight duplicate cells. There you go. And then you can sort your final table by row ID, cell color on top. Now you have that table for only your confirmed. Now you could paste other confirmed ones as well. So as you go through different species, then you can also add these species in the rows until you have a final Excel file. So maybe it's better than using PowerPoint is to use Excel to pull out these tables, paste them together, and then finally have everything you would want in your neg ID, delete everything else, and then you can use this table for statistics because it will have your most confident species. So let's go back to our FluoroMatch Visualizer. Note that I didn't say this before, but I would save this as something else, your FluoroMatch Visualizer, as well as your neg ID fin if you start entering that table. You always want to keep your originals. So we talked about one way of being able to find new PFAS, which is by going through and selecting this A score. Following that, you could also do B plus maybe, and I would stop there as far as scores goes. But if you want other confident series that may show up, I would go to this fragment screener tab over here. In the fragment screener tab, you're going to want to find fragments that you want to screen by. The reason this is a separate tab is that when you select these and you start playing around with this tables, it won't update this, so it will keep them selected. So if you put a lot of work into figuring out what fragments you think are the most distinct and unique for PFAS, and then you can just keep them here and go series by series without it updating and refreshing and taking these off. So for example, here we have pentafluorosulfide, SO2F, SO3F. I'm trying to keep things only with fluorines in them. CF3O, which is related to ethers, CF3, CF2SO3. I know that also C2F5 is a common fragment that's low abundance, as well as all the other chain links. So C5F11, C4F9, C3F7, C2F5, C2FO, again, another ether related lipid. This may be unsaturated ether. So on and so forth. When you're selecting through to find these fragments, again, I would stick to things that are low abundant fragments because these are less likely to match with other non-PFAS masses. The higher in mass you go, the more formula you can get. Also, there's some common fragments that as you go through these data sets, you'll become very familiar. Okay, most PFAS have these fragments, and most noise doesn't. Some fragments, even low mass ones, often show up in noise and can match some common noise masses. Another way to pick these fragments is, again, if we go to the visualizer, you can see that these are sorted by most abundant. Here's this PFAS. It's actually the mass of PFAS, and I guess some other species might fragment to give you a PFAS. So for example, these different masses might fragment. This one is probably a low abundant fragment, so not so interesting. But again, I would stick to those low mass fragments. So here when you see that. So we have SO3F, for example, as a very common high abundant one. We have SF2SO3, C3F7, C2F5. Notice that these will be updated, these list of fragments, if we click on something. So for example, here's a sulfonic acid with a C10, and we click on it. Now we only see those fragments, including the most abundant fragments, which happens to be the N-H here, for that molecule. So I'm going to go back to my fragment screener, and here now it cleans up. So you can see for your visualizer, if we don't have any fragment screening, there's a lot of stuff going on, and we don't know what a series, what's not, especially in these rich regions. For example, over here, maybe I see this neon green series, but it can be difficult even with zooming out, in and out. Notice that their series are colored, so blue relates to one series, this turquoise relates to another, this dark green relates to another. But also note that because there's so many series, it's going to have to recycle through colors. So you can see like a purple here and a purple here and a purple here. It doesn't necessarily mean they're the same series unless they form a straight line. You'll know once you click a series. So for example, one way is you can click over here, and that will show and highlight a different type of series. Clearly no retention time, mass to charge patterns, so probably a false positive. Now, this is a little hard to look through. These orange ones as well, which you can see throughout. This is the CF2 N0 series. So an N0 series is those that don't follow or have any other members in their homologous series. So they don't actually form a series. And so they're out on their own. Now, back to the fragment screener, you can see that it's cleaned up a lot once we looked at some of these common fragments, especially if you look at this retention time versus mass to charge plot. Very hard to see a pattern here. Notice how clear of a pattern there is over here for the PFAS series. They all fall into a very specific range. And that can also be useful to figure out whether something's a PFAS or not. So again, then you would go through one by one through a series. So, okay, what's this series over here? 103. I would scroll back to the visualizer once you find a series, because this doesn't work as well as the visualizer. So just find the series you're interested in, scroll back to the visualizer, type in your 103, find the series here, because there's only 2 members somewhere. Let's see where the other one is. There it is. And then you can click on those fragments. Doesn't look like this has any information, probably false positive. These don't really have much going on. You can see that there's one fragment, so you can actually click on a fragment when you look at the overall to find out which one that was. So it's it's this feature 2422. I'll click it over here. All right, here you go. So now you can see one that showed the fragment. Here's your fragment, which is your C6F13. Pretty low. This fragment 245 does have the right mass defect, 0.91. This one does match a C3F7, I believe, or C2F5 at 168.98. So maybe is a PFAS, but definitely not as confident as some of your other members. And so this is where you kind of have to draw lines based on your own criteria that you set up. But if you see a lot of these correct mass defects, you could say, yes, this is a PFAS, even if I don't know what it is. Because if you scroll through this table, you can see that there's no names for those compounds. So to refresh, we've gone through score as one way to look through annotations. We've looked at just, let's refresh this. We said we can also just look for the series manually in this Kendrick Mass defect region, usually like negative 0.01 to 0.01, or sorry, negative 0.1 to 0.1, even narrower if you want. You'll find a lot of different series there if you have a lot of PFAS. So that's another way, just visually finding these series and then confirming them one by one, looking at score, or we just went over, you can also look by fragments. I shouldn't say or, I'd say and. Use all these methods to find as many series of PFAS as you can. The third method is you can look at number and series. So here's a table of everything. Make sure that you select all scores, that all series and all MSMS files are selected. And now you can look at this table and kind of scroll through this table. And one thing you can do is the number in the series. So here, if we scroll through the number in the series and click the top, now we can see those that have the most members in their series, and that can be helpful too. So for example, this is some kind of ether containing PFAS potentially in CF48. Here we also see an ether and also another ether. And so it looks like we do have this 2 ethers and an alcohol type series, and we can click on one of those again and start to see its fragments. So here's C2F5, C3F7, C9F17, which ends up being also what the precursor mass could be. So here's showing an ether, but we don't have any ether-related fragments. Over here, just carbon-fluorine chain. So that's interesting. So let's look at, for this series, right, series 48, just those members of that series again, right? So we want to start all over again, start annotating this series. You can see again a region that makes sense and maybe a region that doesn't. Notice that the series is right around 0. 0 being no mass defect at all. Also, remember it's normalized to CF2. So something with no mass defect would only have CF2 units, no oxygens, no nothing, which is interesting. And so that's some evidence right there, as well as if we want to look at those that had the most confidence, the Bs, we can look at what the most abundant fragments are. So here we have C13, C11, C12, F23, C14, C3F7, C9F17, C2F5, C4F9. So even though some ether type masses matched, doesn't look like we're having any type of ether type fragmentation like CF30, C2F50. Looks like we just have carbon fluorine fragments. You can see some of the most abundant ones here, C13, 25, C12, F23, C11, F21. Here's a C3, F7, C2, F5. So you can see all of these. And you can then scroll one by one and start to see these fragment patterns. C3, F7, C5, F9. That all have just carbon fluorine chain fragments. And if you look at this, this is the molecular ion, M-H. Here's the mass to charge, or it doesn't have to be M-H. In this case, it looks like an M-. If you look at the C12, F23, should be C12, F24 if it's an unsaturated total carbon. Fluorine only has carbons and fluorines, but looks like it does have an unsaturation here, and just is maybe mono substituted with a hydrogen or a fluorine fell off. And so here we've discovered a new series with an unsaturation, a long carbon fluorine chain without any kind of heteroatoms, and 1 degree of unsaturation. So very interesting. We can refresh this again. And so maybe you do something similar where you look at what's in and out of the range. So let's put in some D pluses too, and you can see that the D pluses, some of those might also be correct. They might follow the same pattern, but they look slightly different. There's a clear pattern here to those that only have carbon fluorine fragments. And this one again could be out of range, but doesn't look like it. So again, you can now export this table. Let's refresh so that we're not only looking at those. Export this table, and then you can name this series as PFC, perfluorocarbon, with 1 double bond, for example, is our tentative annotation there. So let's unselect that series, look at all these series again. Notice that for this 48, this pink one, right by 0, we can also zoom in and see if there's anything related. Sometimes if they're similar in mass defect, they'll be closely related. So let's refresh that. Usually clicking on this. So here we can see another series that's right around 0. This ends up being 51. So let's look at 51. Maybe this is the fully saturated version. I don't know. Let's find out. So again, click over here. Alright, so we see our nice pattern. Interesting that there's should be more isomers as you get bigger, but Let's look at this one. Doesn't have any MSMS. Here's some MSMS. We have C2F5, C3F7. So last time, if you looked at some of the fragmentation, we were seeing things like C3F7. If it was unsaturated, it would be C3F5, something like that. So that gave us some evidence that it was unsaturated. Here we're just seeing the fully saturated forms. And then here's the N-H again, 418. And here you can see that it's fully saturated. So indeed, that is the other series, the fully saturated one. So again, clicking here, see C5F11, C6F13, CF3, C2F5, C3F7, C7F15, so on and so forth. All of these seem to follow the trend pretty well. Some of these don't have fragmentation, so maybe if we want to limit it to only those that have some of these common fragments, you could, or depending on how confident you want to be, you could export all of these, as they all do seem to follow in some nature this retention time pattern. All right, so what were we doing? Just summarizing again, because I know this can be a lot to take in, is we filtered by score, and then you would look one by one at all those series with A's. You can filter by fragments, look at all those series that contain some important fragments. Remember to catalog all these series, because you're going to find the same series multiple ways, because that's how it works if this evidence is real. Then we can sort by the number in series, noting that the structure that it gave, even though it matched the exact mass, was incorrect. We saw that there was no fragments related to ethers, and that there were a lot of fragments related to unsaturations. So we identified this series, C48. Then we'd scroll down and we'd find the next one, 35, which ends up being the PFSA series, and keep scrolling down to the 12, those that tell 12, still F35. Now here's 9. So what's next is going to be, again, we can't go about the exact mass structure that it was assigned, although this is a B+. It's a carbonyl with a sulfonic acid for this 32 series, but it seems like only one thing was given confidence. So let's pull up this 32. Again, this fragmentation looks pretty good. C3F50, that looks like an ether fragment at the third position near C3F5, maybe with an unsaturation you can see as a potential. Here's SO3F, so on and so forth. This is probably the precursor. And so we can pull out this series again, 32. Now it looks really nice in terms of its diagonal. It's a perfect. This is what you'd expect. Some of those other ones look a little suspicious, although they might have a lot of isomers. This is an old AFFF mixture, so that might be what it is. This one doesn't look like it has too many isomers. Although if we zoom in, we can see that there are some isomers here that are very close. And this is a very nice pattern. And then you can see, for example, C3F5, C2F3O2. So only one of them had that ether type linkage. So maybe not ethers. Let's keep scrolling through. Doesn't look like a lot of them have spectra assigned here. Here's C2F3O2, carboxylic acid. Not sure exactly. We don't see any. If we go here, we do see one potentially with a SO3F. You can look at its fragment intensity. It's 149, which is extremely low, so it's in the noise. So probably not real. Yeah, so it's hard to tell from the fragmentation exactly what this species is. It's definitely a PFAS series. We can see this nice trend in this mass to charge retention time plot. We can definitely see some PFAS related fragments with some of the species having a lot of annotations. So here you can see, okay, this is for 326. So this one, yeah, you can see all of those fragments. SO3F. So maybe could be this species. But other ones don't have much. You can see also what some of the other exact methods. So here I would put maybe you could put a tentative PFSA with an oxygen, whether it's an ether or not. We don't know, but that's what that is. And then just put some kind of tentative note, and then again export this and add it to your PFAS. So you keep scrolling down. That was 9, then you go 8, and at some point you stop. Whenever you decide, you can keep going on these data sets. So really, that's the way to dig through your data. If you have any questions or want training in PFAS analysis, remember to contact Innovative Omics, and we're here to help you. Provide trainings both on-site, in person, and virtual. And that should be that. Now I'll just go over some other more advanced parameters if you still want to stay on, but those are the basics. That's all you need to know. You can see this table over here. We have those in the series, so on and so forth. Other things you can do is you can add different columns. So for example, let's say you wanted to see, it's easier to look at if you open the table itself in Excel and see what kind of columns you'd also want to look at. So for example, here we've got the score description, which includes the Szymanski schema. So if you wanted to include that, then you could go over here, scroll up, find, this is in alphabetical order, score description, and you could put it in. And now here you can see your score description. So tentative ID, possible PFAS for this member we look at over here, can be assigned a level 2 after manual review of fragment evidence, provided blah, blah, blah. So you can get some idea of how to look through that better. Level 5, possible ID, possible PFAS, 3 plus an homologous series, at least one highly likely PFAS identified within a homologous series. So on and so forth. Note that that doesn't take into account your manual review of retention time, mass to charge patterns, things of that nature. And so this is just a tentative assignment of Szymanski level. You'll be able to give a more confident assignment by looking over it manually. Some other columns of interest, for example, could be while we're showing frags, there's also other fragments that don't show up in the screening method. So you could add, for example, this frags.1 has a number of other types of frags, as well as this column has different types of fragments. And then also if you wanted to know like what all the possible different PFAS are, especially for level A or Bs, you could go to this potential and it will give you multiple ones as well. And so you could add this onto your table. Might get a little lengthy and hard to deal with, but it's an option for you. You could also see the number of frags right away. So let's say we want to add the number of frags, would be interesting. Here's number of frags.1 is going to be using fragment screening as well. So again, you have to click your table. Then you can add number of frags. interesting. Now we can kind of sort them by the number of frags, which could be a pretty powerful tool as well. Making sure we're in all the series, all the scores, so on and so forth. Looks like it's a little hard to sort. Yeah, so it's not sorting it as a number because it's a character. So you'd have to do a little bit more things, but you could easily like click on something right away that you find, okay, this one has 25 frags. This is 38. It's an unsaturated sulfonic acid. Oh, that's another one. So now we can look in the unsaturated sulfonic acids, so on and so forth. So again, contact me, innovativemics.com, or contact us at Yale. And thank you for watching.